NASA just released 20 images that change everything we thought we knew about the universe. Black holes devouring stars in real time. Galaxies gliding 300 million light years away. And something on Mars that shouldn't exist. These aren't artist renderings. They're real photographs. And some of them reveal phenomena scientists have never seen before. December 2024, NASA's imaging archive goes public with a collection that's been classified for months. 20 photographs captured by the James Webb Space Telescope, the Hubble Space Telescope, and Mars rovers. Each image represents months of observation, thousands of hours of data processing, and discoveries that challenge our fundamental understanding of cosmic evolution. What you're about to see isn't just beautiful. It's evidence. Evidence of stellar birth in regions we thought were sterile. Evidence of chemical processes that might indicate life. Evidence that the universe operates in ways our models haven't predicted. Image 1 takes us 13.4 billion light years away, to a moment just 400 million years after the Big Bang. Webb captured a galaxy cluster designated Glass Z13. But this isn't just another early galaxy. Look closer. Those bright cores scattered throughout the frame. Each one is a supermassive black hole, active, feeding, growing. The problem, black holes this massive shouldn't exist this early. Current physics gives them about 1 billion years to form and grow. These existed in half that time. Either our timeline is wrong, or black holes formed through a mechanism we haven't discovered. Dr. Rohan Naidu from MIT analyzed this image for 3 months. His conclusion, we're missing something fundamental about the first epoch of the universe. The structures here are too organized, too mature, as if someone fast-forwarded through cosmic evolution. Images 2 through 5 shift from the ancient universe to stellar birth happening right now. Image 2, the Carina Nebula. Webb's infrared sensors pierced through dust clouds that blocked Hubble's view for decades. What emerges is a landscape of creation. Pillars of gas and dust 20 light years tall. And buried inside, hundreds of protostars, stars in the process of igniting. You can see the shock waves. Radiation from nearby massive stars compressing the surrounding gas, triggering new star formation, a cascade effect that turns nebulae into stellar factories. Image 3 zooms into one pillar, enhanced to show temperature gradients. The hottest regions glow blue, over 10,000 degrees Celsius. Cold molecular clouds appear red, minus 260 degrees. The boundary between them is where stars form, where gravity overcomes thermal pressure and collapses gas into fusion reactors. Image 4 reveals something unexpected. A brown dwarf, an object too small to sustain hydrogen fusion, but too large to be a planet. This one is only 13 Jupiter masses. It should not have formed here. Brown dwarfs require different conditions than stars, yet here it is, nestled among protostars, suggesting the formation process is more chaotic than models predict. Image 5 pulls back to show the full Carina region, 300 light years across. You can see the life cycle of stars compressed into one frame, molecular clouds on the left, protostars forming in the center, massive blue giants on the right already begin. Images 6 through 9 document violence on the largest scale. Galaxies in collision. Image 6, the Antennae Galaxies. 2 spiral galaxies locked in gravitational combat 45 million light years away. Webb captured them mid-merger. You can see tidal tails, long streams of stars ripped from both galaxies by tidal forces. Each tail stretches 100,000 light years into space. But the collision itself is creative destruction. The compressed gas between the galaxies glows brilliant blue. Star formation triggered by the impact. Thousands of new stars per year. 10 times the rate in the Milky Way. Image 7 focuses on the collision core, where the two galaxy centers are merging. Each galaxy has a supermassive black hole. As the galaxies merge, so will the black holes. This process releases gravitational waves, ripples in space-time detectable across the universe. We're watching the future of our own galaxy. In 4 billion years, the Milky Way will collide with Andromeda. These images show us what that looks like. Image 8 captures a ring galaxy, cartwheel galaxy, 500 million light-years distant. This isn't a natural ring. It formed when a smaller galaxy punched through the disk of a larger one, like a stone dropped in water. The impact sent a density wave propagating outward. That wave compressed gas and triggered star formation in a perfect ring 150,000 light-years across. The ring is temporary, and another 200 million years, it will disperse. But right now, Webb caught it at P. The ring is temporary. In another 200 million years, it will disperse. But right now, Webb caught it at P brightness. The blue ring contains millions of massive hot stars, all born within the last 10 million years, all created by a single collision event. Image 9 shows the aftermath. A merged galaxy, designated NGC 7252. The collision finished 100 million years ago. What remains is an elliptical galaxy. No spiral arms, no organized structure. Just a smooth distribution of old stars. This is the final state. After the fireworks fade, after the star formation ends. This is what Milky Way and Andromeda will become. Images 10 through 13 bring us closer to home. Exoplanets and their host stars. Image 10, WASP-96b, a gas giant orbiting a sun-like star 1,150 light-years away. But this isn't a photograph of the planet. It's a spectrum. When WASP-96b transits its star, some starlight passes through the planet's atmosphere. Webb analyzed that light and found water vapor, clouds, and signatures of photochemistry. This is how we characterize exoplanet atmospheres, not by seeing them directly, but by reading the fingerprints in starlight. Image 11, a protoplanetary disk around the star HL Tauri, 450 light-years distant. The disk shows concentric daps, rings carved by forming planets. We can't see the planets yet. They're still too small. But their gravitational influence clears paths through the disk, like wakes behind invisible ships. This image is the closest we've come to watching a solar system form in real time. Image 12 captures something remarkable, a debris disk around the star Fomalhaut, only 25 light-years away. Previous images showed a smooth ring, but Webb's infrared view reveals structure, multiple rings, eccentric orbits, and one massive clump. That clump is probably a planet, a super-Earth or small Neptune, carving through debris left over from planetary formation. Dr. Andres Gaspar at the University of Arizona estimates the planet is about twice Earth's mass, and it's shepherding the debris into these complex patterns. Image 13 is a direct image, an actual photograph of an exoplanet. HIP 65426b, a gas giant 15 times Jupiter's mass, orbiting 92 astronomical units from its star. That's 3 times the distance from the Sun to Neptune. This planet glows in infrared, still hot from its formation. Young planets emit their own light, making them easier to photograph than old, cold ones. But the significance goes beyond the image. Webb can now directly image planets and systems too young for life, track their formation, measure their atmospheres, and determine which ones might eventually host habitable moons. Images 14 through 16 come from the ground. Mars rovers capturing details invisible from orbit. Image 14, Perseverance rover photographed layered sedimentary rock in Jezero crater. The layers are diagonal, tilted at 15 degrees. This isn't how sediment deposits, unless water was flowing. Fast-moving water carrying sediment and depositing it in slanted beds. This is direct evidence that Jezero crater was once a river delta. Water flowed here for thousands of years, long enough to deposit meters of sediment, long enough, potentially, for life to establish itself. Image 15 shows the rock up close. Perseverance used its abrading tool to grind away weathered surface layers. Underneath, green-tinted minerals. Olivine mixed with iron oxides and clays. This combination forms in the presence of water, and the specific chemistry suggests pH-neutral water, not acidic, not alkaline. Water that life could tolerate. Image 16 is the most controversial. A small nodule photographed by Curiosity rover in Gale crater. The nodule is spherical, about 1 centimeter across, hollow, with a thin shell. On Earth, structures like this form through two processes. Concretion, where minerals precipitate around a nucleus, or biological activity. Shells, egg cases, microbial colonies that mineralize. NASA was careful in the press release. They called it a concretion. But the image sparked debate, because the nodule's surface has patterns, repeating structures that look organized, not random. Dr. Abigail Allwood, a geologist on the Curiosity team, stated that more analysis is needed. The rover can't determine composition from photography alone, but the nodule is now a high-priority target for future sample return missions. If this is biological, it changes everything. Images 17 through 19 show the universe at its most destructive. Image 17, a supernova remnant. Cassiopeia A, 11,000 light-years away. This star exploded 340 years ago. The blast wave is still expanding. Traveling at 5,000 kilometers per second, Webb captured it in infrared and found something new: dust. Enormous quantities of dust forming in the expanding debris cloud. This dust is the raw material for future planets. When stars explode, they forge heavy elements: carbon, silicon, iron. These elements condense into dust grains. The dust spreads through space, mixes with gas clouds, and eventually forms new solar systems. Every atom in your body heavier than hydrogen came from a supernova. This image shows that process happening, the birth of future worlds from the death of a star. Image 18, a tidal disruption event, a star torn apart by a black hole. This happened in a galaxy 250 million light-years away, but Webb caught the aftermath. A stream of gas spiraling into the black hole, heated to millions of degrees by friction, glowing in X-rays and ultraviolet light. The star was probably sun-like, wandered too close to the black hole. Tidal forces stretched it until it ruptured. Half the star's mass fell into the black hole. The other half was ejected at 10,000 kilometers per second. This is how black holes feed, not by vacuum sucking everything nearby, but by shredding objects that stray too close. Image 19, a gamma-ray burst. The most energetic explosion since the Big Bang. This one occurred 7 billion light-years away. A massive star collapsed, Its core formed a black hole. Jets of matter erupted from the poles at 99.9% light speed. When those jets slammed into surrounding gas, they released energy equivalent to 1 trillion suns. For a few seconds, this event was brighter than its entire host galaxy. Webb captured the afterglow. Days after the burst, the jets have slowed, but they're still visible, carving tunnels through the interstellar medium. These jets sterilize space. Any planets within 10,000 light-years are irradiated beyond habitability. Gamma-ray bursts are extinction events on galactic scales. Image 20 is different. It's not one object. It's everything. Webb's deepest field to date. A patch of sky smaller than a grain of sand, held at arm's length. Observed for 200 hours. The image contains 45,000 galaxies. Each one, billions of light years away. The farthest objects in this image are 13.5 billion light years distant, light that left when the universe was only 300 million years old. You can see spiral galaxies, ellipticals, irregulars, galaxies merging, galaxies being torn apart by tidal forces, every stage of galactic evolution captured in one frame. And between the galaxies, nothing. Not darkness, but the space where light hasn't reached yet, or where galaxies are too faint to detect. This image is a census, a measurement of how many galaxies exist. Based on this one tiny patch, astronomers estimate 200 billion galaxies in the observable universe, each containing 100 billion stars. The numbers stop making sense. The universe is larger than human cognition can fully grasp, but we can photograph it. We can study it. And with each image, we understand a little more. 20 images, 20 windows into the cosmos. From the first galaxies born in the ancient universe to dust forming on Mars today. From stellar nurseries to colliding galaxies. From exoplanets to gamma-ray bursts. Each photograph is evidence. Each one tells a story written in light that traveled from millions or billions of years to reach us. NASA's archive will continue growing. Webb will observe for another decade. Hubble still operates. Mars rovers keep exploring. And each new image won't just be beautiful, it will be data, evidence of how the universe works, and proof that we're only beginning to see what's out there. The next release might answer questions these images raised, or it might reveal something even stranger. Either way, the universe isn't finished surprising us.